This is video 5. We present here the definition of pumpability and the main result of our article. Along this video, we will use the following tile set to build our examples. This is the tile set introduced at the end of video 3. Also, we will use this tile assembly system. The seed is represented in black. This is the directed tile assembly system introduced at the end of video 3. Now, consider the following simple path assembly P. This path assembly is producible by the tile assembly system. Consider the segment in gray of the path assembly P. This segment starts in PI1 and ends in PI2. The path assembly P is made of 3 parts. The beginning of P, which starts at P1 and ends at PI1. The candidate segment, and the end of P, which starts at PI2 and ends at the last tile of P. According to the tile set, the segment in gray is a candidate segment of P. Then, let's try to build the extension of this segment. Here we have built an infinite path assembly by concatenating the beginning of P with the extension of its candidate segment. The beginning of P is in white and its extension is in gray. Moreover, this infinite path assembly is producible by the tile assembly system. In this case, let's remark that the same thing can be done with the extension of P in the other direction. We obtain another infinite path assembly. We say that a candidate segment of P is pumpable if and only if at least one its extension can be produced by the tile assembly system. A path assembly is pumpable if and only if there exists a pumpable candidate segment of P. The notion of pumpability is the key notion of this study. Our aim is to find pumpable segment in a path assembly. Now, we focus on the obstacles which can prevent a candidate segment to be pumpable. Consider another path assembly P' and a candidate segment of P' in gray. P' is producible by the tile assembly system. The concatenation of the beginning of P' with the extension of the candidate segment is a path assembly producible by the seed. Then, this candidate segment is also pumpable. Nevertheless, remark that the path assembly produced by this concatenation is not simple. Look at the position with a black dot. This position is occupied by 2 tiles. One belongs to the beginning of P' and one belongs to the extension of the candidate segment. In our example, these 2 tiles have the same tile type. Suppose now that these 2 tiles have a different tile type. In this case, the candidate segment is not pumpable in this direction. Let Q be the extension of the candidate segment. Then the tile Q0 is equal to the tile P'I'1. We define the first inconsistency of Q as the first tile of Q which is not producible by the tile assembly system. The first inconsistency allows us to find an obstacle which prevents the candidate segment to be pumpable. Remark that this obstacle does not belong to the end of the path assembly P' since this part of the path assembly is not relevant in the concatenation. If the candidate segment is good, then Q is a path assembly. In this case, the first inconsistency occurs either in a position occupied by a tile of the beginning of P or by a tile of the seed. If the candidate segment is not good, then Q may not be a path assembly. In this case, Q is only a sequence of tiles. Then the first inconsistency occurs either in a position occupied by a tile of the beginning of P or by a tile of the seed or by a tile of the candidate segment. This property is due to the periodicity of Q. Finally, the main result of this article is the existence of a bound which depends only of the size of the tile set and of the size of the seed. We prove here that any simple path assembly growing at distance more than this bound to the seed is pumpable. In this example, any simple path assembly growing outside the hashed rectangle is pumpable. Note that this article contains several bounds. The definitions of these bounds are given in an appendix of the article available online. Now let's discuss about the consequences of the main result. Our true final result is that a tile assembly system cannot simulate a Turing machine at temperature 1. For example, consider the directed tile assembly system used as an example along this section. Let alpha be its unique terminal assembly. This infinite assembly is described at the end of video 3. we claim that our result implies that the structure of alpha is simple to describe. Now, consider the finite assembly beta 1 which is in dark gray and the finite assembly beta 2 which is in light gray. Also consider the two vectors v and w. Consider a position of the grid u which belongs to the domain of alpha. First, we wonder if there exists an integer I such that the translation of u by iv belongs to the domain of beta 1. For example, consider the position u with a back dot. By translating this position by 2v, we obtain a position occupied by a tile of beta 1. The type of this tile is T15. Then the position u is occupied by a tile of type T15 in the assembly alpha. Now suppose that there exists no I such that the translation of u by iv belongs to domain of beta 1. Then in this case, there exists an integer I and a positive integer j such that the translation of the position u by iv plus jw belongs to the domain of beta 2. Consider the following position u. By translating this position by 2v plus 2w, we obtain a position occupied by a tile of beta 2. The type of this tile is T22. Then the position u is occupied by a tile of type T22 in the assembly alpha. In this example, we can characterize the assemble alpha using two finite assemblies and two vectors. We claim that if our main result is true, then it is always possible to characterize the unique terminal assembly with a bounded number of finite assembly and vectors. In fact, in the article entitled Limitations of Self-Assembly at Temperature 1, the authors have already shown this final result assuming that all path assemblies large enough are pumpable. Nevertheless, there exists a subtle difference in our definition of pumpability and the one used in this article. The definition of pumpability used in this previous paper consider a path assembly which is a sub-assembly of the unique terminal assembly alpha, whereas we consider here a path assembly producible by the seed. In our case, the path assembly has to intersect with the seed to be pumpable. This hypothesis is not required in the previous article. Nevertheless, we can provide a proof of the final result with only slight modifications of the tools developed in this previous article. Then the combination of these two results leads to the fact that computation cannot be done at temperature 1. The final result will be added in the appendix of the article available online.